Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 3 for this week, and we're going to be talking about how vertical wind shear can contribute to the formation of severe thunderstorms and tornadoes. And there's a couple of different ways that we're going to look at that today. And so let us go on ahead here and take a look at approach number 1. So again, the green area is my poor man's representation of the ground. And let's suppose that you're looking toward the north and there are westerly winds blowing and they're lightest at the ground, and then they gradually increase in speed as you go up through the atmosphere. So this is what we call vertical wind shear, and that can occur in two different ways. You can either increase the speed as you go up, or you can also change the direction as you go up, or both. Okay, so there's actually, I guess, 3 possible combinations there. And you can also have negative wind shear. It doesn't always have to be positive. The wind can decrease with height, or it can, instead of veering or turning more clockwise with height, it can turn counterclockwise with height. And usually when it's veering with height, we're in a situation called warm advection, where we are trying to transport warmer air into our region. And then if they back with height, like for instance, let's say it's northwest at the surface and west aloft somewhere and then southwest above that, that's cold advection, and that means that cold air is, or colder air is actually moving in. So that's another way you can interpret that. Okay, so you have the vertical wind shear, and so this creates what we call vorticity or spin, but that spin is about a horizontal axis. Well, are tornadoes spinning about a horizontal axis? No, okay? They rotate around a vertical axis. So how does vertical wind shear contribute to the formation of rotating thunderstorms, rotating updrafts, and tornadoes? So this is the process. So again, we're looking toward the west, so the wind's coming right at you, and if you were really, really tall, your feet would experience lighter winds than your head, but that's obviously a bit of a stretch. Okay. So that black line represents the axis of rotation, and you have the rotation coming up from behind that line, over top of it, and then cutting back underneath. And so the spinning is like this, but again, it's about a horizontal axis and not a vertical axis. So how do we change that? Well, what happens is that we have an updraft that comes along with a thunderstorm, okay? And that updraft tilts that, what we call vortex tube, the axis of rotation about the horizontal, and it basically bows it upward, okay? And so on the south side of the storm, you end up getting rotation about a vertical axis in a counterclockwise manner. And then on the other side, on the north side, you have rotation in a clockwise manner, okay? All because this updraft tilted this axis of rotation into the vertical, okay? And so as a result of that, you actually get couplets, one rotating cyclonically, one anicyclonically, and the anicyclonic one every now and then can produce a tornado, but it's much, much more common with the cyclonic rotation part of the couplet, which is this thing right in here, and that usually evolves on the south side of the main updraft. So basically, all we're doing here is taking rotation about a horizontal axis, an updraft comes along, tilts that axis into the vertical, and then you end up getting rotation about a vertical axis, both counterclockwise and clockwise. Now, another way to look at wind shear that meteorologists use commonly is called a hodograph. And this is what we call a polar coordinate system here. Okay, it's not X and Y like a graph, but it's polar coordinates. And so all of the winds that you plot originate right here at the origin and the center, okay? And you know how I've talked about, I think, in the past, where the weather observation, if it says the wind is southwest at 10, that means the wind is coming from the southwest and blowing toward the northeast. On this type of diagram, you actually want to draw the arrow toward the direction that the wind is blowing, okay? Not the direction it's coming from, but the direction that it's blowing toward. So here we have a set of data. This is, I just made this up, okay? So we're looking at 0 kilometers surface, 2 kilometers, 4 kilometers, and 6 kilometers. So let's plot the one first from 160 degrees at 20 knots. So we start at the origin, and then each one of these circles represents 10 knots. And so we blow it from 160 degrees which would be this angle right in here, and then extend it up to the 20-knot circle, and then we've got our surface wind there, okay? Now the next one is 228 degrees at 30 knots. So again, we start at the origin, we go 10, 20, 30, and that arrow goes out to here. Then at 4 kilometers, we're 244 degrees at 45 knots, and so that goes this way up to the middle between the 40 and the 50. And then finally, we've got a wind from 250 degrees at 60 knots, so that goes all the way out to the outer circle. Now, if you drew a line or an arrow from this endpoint to this endpoint, that is called the shear vector, okay? And it represents the amount of shear in the layer between 0 kilometers and 2 kilometers. And then if you connect these two, that's the amount of shear between 2 and 4, and this one between 4 and 6. And if you connect all those lines, this is what you get. And although a straight hodograph like this, that purple line that's straight, while that wind distribution, if you will, can create supercells, okay, it's not nearly as common as if the hodograph is curved, okay? So the winds are actually increasing in speed and veering with height, okay? They're turning clockwise with height, but the wind shear vector from the surface all the way up to 6 kilometers is straight, and that is not a terribly favorable situation for the formation of supercells and tornadoes. So let's look at another example here. So our surface wind is going to be 160 at 20 again, okay? Now our 2 kilometer wind is going to be 190 degrees at 33. Our 4 kilometer wind, 215 degrees at 45. I know it looks like it's just slightly beyond 45 there, but it's close. And then 6 kilometers, 250 at 60. Now, if you connect each one of those shear vectors, you get what we call a curved hodograph, which is much more favorable for the development of rotation within the thunderstorm. And the area that is swept out between this purple line, the surface wind, and the top wind, this area in here, is you can measure the amount of what we call helicity in the atmosphere, okay? And helicity is another word for rotation or spin. But the bigger area that is swept out, okay, like if we have a straight hodograph, then that area is not going to be nearly as big. But when it's curved like this, it increases the area quite a bit, and it sets up a distribution of mass that actually makes it easier for that rotation to commence. Now, it used to be that we would look at the 0 to 3 kilometer layer to look at tornado potential, but more recent research has shown that really, in order to get a tornado touching the ground, which I should have said that differently, a tornado is rotation that is touching the ground. If it's the loft, then we refer to it as a funnel cloud or something like that. But anyway, more recent research has shown that you actually want a tremendous amount of wind shear in the lowest kilometer. In fact, there's even been more recent research that indicates that it boils down to the lowest 500 meters, or about half a kilometer, okay? So 0 to 3 kilometers is a good measure of whether or not you can get a rotating supercell, but if you really want to take a look at the tornadic potential, then you really have to get into that lowest layer, either 1 kilometer deep or 500 meters deep. And if you have a lot of rotation or a lot of change in the wind over that relatively shallow layer, then that is a situation that can lead to not only tornadoes, but violent tornadoes if the shear is strong enough. So basically what I've done today is share with you a number of tools that meteorologists use to assess severe weather potential. And you can either look at current observations, like when the weather balloons go up at all these various spots around the world, you can assess what the current state of the atmosphere is, and then the numerical models will give you forecasts as to what that hodograph will look like at different times. And that's one of the tools the Storm Prediction Center in Norman, Oklahoma uses when they're trying to decide on their overall severe weather outlook for the day, and then more specifically where they're going to issue watches for various parts of the country. Alrighty, I know that was a bit detailed, but hopefully that was at least somewhat interesting. That is bonus weather video number 3 for this week. The next one will be coming up on Monday, of course, and the next daily update coming up Monday as well. Beautiful weekend coming out. Get out and enjoy it if at all possible. And we will see you again on Monday. So have a great rest of your Friday evening, not much left, and an even better weekend. See you, everybody.